this is Stampy. Who has kids who watch Stampy on YouTube? No one? 1, 2, 3. Only 3 people? 4? I saw another hand. Who has kids? Put your hand up if you have kids. Who has kids who play Minecraft? Who has kids who play Minecraft who watch Stampy on YouTube? Hello! This is Stampy. Welcome to another ASP.NET 5 video. All right. I just can never get it out of my head because every morning while I'm making my coffee, there's one kid parked in front of the TV watching Stampy on YouTube. Although the argument is that I actually quite like them playing Minecraft because it's very creative. It's so much better than the other crap that I played when I was a kid. And it's better than watching Netflix, right? They can play Minecraft and stuff, and they like watching other people play stuff. It never occurred to me when I was playing video games as a kid that would be a thing, but it is. All right. Let's talk about performance. Did anyone enjoy the first 2 sessions? I mean, they're completely random ideas, but I had some feedback that people really appreciate that we just spitball ideas out. But does everyone kind of think that that's a good use of your time coming up here where we just, okay, good. Because I mean, some of the little pieces of those ideas are in GitHub issues, but they're kind of lost in the backlog. Like we never really have a chance to just bring them into cohesive ideas for 1 hour and just talk about them. So this is what I'm trying to treat today as. Yes. Okay.
Is to see those, participate in those discussions.
Great.
Most of the stuff I can learn online, no problem.
Okay.
But those kind of discussions,
you can't have really unless you're here. Okay. Great. I'm glad. So now I'm going to talk about performance because we've been doing a lot of really, I mean, I've been enjoying it, a lot of enjoyable work on performance. And who watches the community stand-up? Right. Okay. Good. So we've talked about some of the stuff I'm going to talk about during that episodic thing that we do every week with Hanselman and Hunter, with Galloway, sorry. So let's have a look at what we're talking about. So ASP.NET has probably never really been considered as a very fast framework, like one of the ones that is right up there. It's certainly not slow. But when we look at the modern web and HTTP server landscape, a lot has happened in just the last couple of years that has really changed the game about what we consider to be a fast, lightweight, add any other type of adjective in there that is remotely relatable to performance framework. So we have a lot of work to do, and we've made some changes in ASP.NET 5. I talked about Kestrel yesterday, which gives us some opportunities to fix some things that we perhaps haven't been able to fix before. And I want to talk about those. I want to discuss why this is interesting. I know there will be people in the audience who think this is just pointless. Why do you care about benchmarks? There are reasons for doing these things. So what types of performance are we talking about? So startup time is a big one. MVC 5, file new, wasn't particularly great startup time. You deploy it to Azure, file new, Visual Studio, deploy to Azure, and after you wait the 3 minutes for it to deploy, the startup time may take you anywhere from 10 to 20 seconds, depending on the app. That's not great. Like, we want the app to start up a lot quicker than that. I had a customer last year who had a fairly sizable MVC and web forms application that their app took 47 minutes to start. To start, like, amazing. So imagine trying to do continuous development, continuous deployment in that model. Like, I want to make a change, and now I want to verify, like, I want to look at the change. It takes 45 minutes to start the app. And that was because they were doing some crazy things, but not that crazy. They had like 700 assemblies in the bin folder. Everything was a view control or a partial, which meant they had 1,000 partial files. They all have to be compiled at app start because they were doing pre-compilation, all these type of things. And because of the old compilation model in ASP.NET 4, where we shelled out to csc.exe and we didn't reuse anything between compiling folders, you would pay all this cost of loading 600 assemblies from the bin folder to invoke one view. Right, that one's done. Now let's do the next one. Load 600 assemblies from the bin folder and invoke that view, and then multiply that by 1,000 views, right? That takes a long time. So with the Roslyn-based compiler, we fixed a lot of that. But these are the things that can contribute to startup time, like the host booting the CLR. In IIS, it used to be Helios. Before that, it was System Web. Now we have a new host. Today, it's DNX. After RC1, it'll be the .NET CLI, whatever that ends up being called. So you have to boot the CLR, you have to find and load all the dependencies of the application. Are they in the bin folder next to it like they used to be? Are they in a packages folder somewhere else on disk that I have to enumerate and load? Can I just look in a metadata file like project.lock.json, parse that file, make sure all the versions are correct? And there's a lot of work that goes into just starting the CLR and then finding and actually running the method in the application or in the DLL that is the entry point. That all takes time. JITting dependencies. If the dependencies are IL, you need to JIT them. Who has noticed that on sometimes after you deploy to Azure or if you're on a machine and you've gotten to a certain situation, starting a very basic application, ASP.NET 5 from the command line can take like 5 seconds before you see something happen? Who's seen that? Or even longer. Like live ASP.NET Beta 7, after I deployed it, would take 45 seconds on Azure before it would come up with the homepage. Most of that time was spent JITting Roslyn. Because Roslyn is huge. It's a really big assembly. It's all IL, so when you load it into the CLR, the jitter has to turn it into assembly, right? Native code. And that takes a long time. That's one of the advantages of things like .NET Native, where you can do that ahead of time. You've probably also heard of NGen, which lets you pre-JIT stuff, but there's a lot of rules about when you can NGen and what happens when you NGen. There's a new thing called cross-gen that we use in a DNX that lets us do certain things, and there's more ideas of how to make this better in the future, but the point is JIT costs time. And it costs time before your app actually starts. The ASP.NET layer, so once you get through all of that, and now I'm actually running ASP.NET code, there's all the code in ASP.NET that isn't your code, right? So the host has to boot up, it has to find your code, it has to do all the ASP.NET things, start up the server, blah, 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 open sockets, all that type of stuff has to happen. And we want to make that as efficient as possible. And then finally, you have the code that you actually wrote in your startup class, that configure, constructor, configure services, that all has to be called before the first request and has to return before the first request can actually be served. Okay, so a lot has to happen from the time you hit enter in the command line before the first request can actually be served. And we want to make that as small as possible. Throughput. This is probably one of the first things people think about when they think about performance. What are the things that affect throughput? How fast, how many requests per second can my application do? Obviously, architecture plays a big part in this. You're going to hit walls very quickly if you haven't architected your application to provide good throughput as you add more and more load. That means architecture in our layers, right? In ASP.NET, HTTP, all those things, in the servers, as well as obviously in your application. But at the moment, I'm really talking about us, ASP.NET. The algorithms that we use to do stuff obviously affect throughput. How do we parse HTTP headers? Right? That's obviously a very complex thing. It sounds simple if you just assume someone else is doing it for you. That used to be the case. IIS or HTTP/sys used to do it for us. But in the cross-platform world with Kestrel, we have to do all that work now. That's what writing a web server really means. You have to parse headers. You have to frame messages. You have to put them in order and then send them back out again. That's expensive. You're taking bytes off the wire and then interpreting them as ASCII, if they're a header, according to a spec that's defined by the ether, and then representing that in an object model that the application can consume. HTTP context, HTTP request, headers collection, cookies collection. To get from bytes on the wire into those things takes a lot of time. Okay? And so what we do there has probably one of the biggest impacts on how quick our benchmarks run. Caching is obviously really important. If we do something that's computationally expensive and that can be reused, obviously we want to cache that. Now that has side effects. When you cache stuff, you use more memory, which affects GC, which is the death of performance in most managed applications. Okay, you have to really think about that sort of things. But caching is obviously really important because we don't want to do expensive things more than once if we can. Optimizing system calls. This is a really big one now that we have our own web server that is built on top of a native library. Every time that you make a call from user mode into kernel mode, a system call, there's cost. There's operating system cost involved. There are interrupts that get fired in the CPU cache flush lines get cleared, all these checks and boundary conditions get done by the kernel. This happens all the time, like thousands of times a second, but when you're trying to build web servers that can benchmark at millions of requests per second, which is where we are now in today's landscape, this will kill you. Like, you need to figure out how to reduce the amount of transitions you make from user mode to kernel mode. With HTTP/sys, because it's a kernel mode driver, which gives you a lot of benefits, it means that every time you call in to do anything HTTP-ish in IIS and using HTTP sys, you're doing a sys call. Okay, so you have to pay that cost. So there's really a glass ceiling involved when working with HTTP sys, and I can show you some numbers later where you hit that because of you just can't get rid of these transitions. They're there. You cannot make them go away. And there are things you can do if you own the full stack end to end, all the way down to the socket, that you can do to fix that. Obviously, optimizing memory allocations is the last and hardest thing to do when building a very fast web server and a very fast web framework. You know, in managed frameworks like .NET, GC is something you always have to be cognizant of. Always. Gen 0 GCs, yeah, they're pretty cheap. You can do those pretty safely. Things in Gen 1, not so bad. Okay, you still don't really want to be having to do Gen 1 very often, but you can live with those. But Gen 2, like getting stuff into Gen 2 and running out of space in Gen 2 because objects are living too long, and then having to pay the cost of doing a Gen 2 collection is death to an application, a web application. Gen 2 will generally pause. Okay, even with background and multi-core garbage collection, you really want to try and limit the number of Gen 2. And then you've got the large object heap, which is just a whole other ball game, which is really, really dangerous. Then pooling. This is what we see a lot of the very, very fast managed web frameworks are doing today, is they pool everything. Everything. Every time that you get a request come into the application and you get given an object that represents that request with a whole bunch of API that hangs off it, generally nothing was created as a result of that request. They just reuse one they created before, null it all out, and just put all the data in after they've serialized it and parsed it off the bytes off the wire. Okay? That is fast, but very difficult to get right. It's dangerous because if you don't reset stuff properly, you start having state leak from one request to another, right? So you can have a query string parameter that was on one request appear on a different one because the code that we wrote to reset the object so that we could pull it and reuse it had a bug in it. And as we go over time and the product has to add more and more features to those things that are pulled, you have to be really careful that when you reset that object, you can reset it quickly, you do it at the right time, and you reset all the state that you have to. So pooling is very powerful, but is also very dangerous. Now, we do pull a lot of things today. Even in old ASP.NET, there were certain intrinsic objects that were pulled. The HTTP application object was pulled. Okay, it was well documented that it was pulled, so it had certain behavior. HTTP handlers could be pulled. Remember that property on the handler called isReusable that no one really knew what it meant, so you just set it to false because I don't know what it does. Effectively allowed the runtime to decide whether it would pool instances of that because they can be expensive to create. So pooling is important. What about latency and response time? This one is generally a direct impact on user experience. Okay, like if you're sending stuff down to the browser, and there's a user or to a mobile phone and people waiting on it, this will directly affect your user experience. It also has an effect, obviously, on how much throughput you can get. Because if you're testing with a fixed number of clients and there's a certain amount of latency and those clients have to sit around doing nothing while they're waiting for that latency to elapse, you're not getting any throughput at that point, right? You have to, so latency has an effect on everything. Again, architecture is important. The algorithms we do, again, are important here. Caching is really important here because it reduces the amount of compute we have to do. And I/O management is really important here. Like when you start doing asynchronous I/O, there is a big gap between when you start an operation and when the operation completes. And just because the operation completes doesn't mean that you know it's completed. All right? In that .NET makes this all look magical. Async await, blah. I get told immediately when it's completed. Not really. You get told when the underlying infrastructure has figured out that it's completed. That doesn't mean you get told the exact instant that it was completed. Because you just don't. I mean, those things are happening on different threads. Someone has to marshal the data from one place to another and be told that it was marshaled so that they can go and get it to give it to you. Generally, that is not push. Right? Otherwise, that would just burn CPU all the time, and it's not polling in a tight loop because that also burns CPU. It's generally timer-based and it's generally queue-based, and so there is always latency involved in those things. And when you get right down to the I/O layer and interoperating with things like libuv, managing this is critical in order to get really good response time. Scale. How does the application behave as we add more connections to it? Right? That's what I mean by scale here, or concurrency. Again, architecture is really important. Right? Optimizing memory allocations here is super important because if you're not doing good memory management where that memory is assigned per connection or per user, then if you get more users, you just start bleeding memory, right? You'll quickly hit a limit. You say, yes, my application is really fast. I allocate 5 megabytes per request, but those requests finish really quickly. So that's great, but if you're allocating 5 megabytes per request and I get 100,000 requests come in, you're going to have a problem, all right? So everything in performance is a trade-off. And then obviously, effectively using CPU cores also helps you scale, because if you've got 16 cores or 32 cores in your server and you can use them all, you can do more things concurrently, and thus you can potentially handle more requests at the same time, okay, without lots of scheduling and overhead and queuing and all that type of stuff. Working set is something that comes up a lot as well. This is one of the massive benefits of things like native compilation, is that we can reduce the overhead, just the memory overhead of the process once it starts. In .NET's memory management system and garbage collector aggressively allocates memory, okay? Because it's cheaper to ask for memory up front than to ask for lots of it, than to ask a little bits of memory all the time, okay? And so you'll often look at a .NET application and it'll have lots of memory reserved, but when you run an analyzer on it, like a profiler, you'll say, oh, I'm only actually using 2 megabytes of heap space or 60 megabytes of heap space. You go, that's funny. Why is my process using 500 megabytes? Okay, because there's a lot of native memory that was allocated by .NET to do all the memory management for you. So again, being able to optimize that is something that we have to think about when we want to be able to say, hey, you can host lots of applications on one web server, because the cost of starting that application is low, because our working set or our memory overhead of just having the application start is low. Again, .NET Native is really the big win here, if we can get to a point where that will work for us. All right, so define some things. Benchmarking versus real-world performance. Well, I've talked about this on the stand-up before. Like Scott and I sort of riffed about this on the stand-up, about what's the point in doing benchmarking, like Tech and Power, and we'll talk about that in a minute. That doesn't reflect real-world performance at all. And it's true. Like, to a certain extent, benchmarks, micro benchmarks, or platform benchmarks don't necessarily represent real-world performance, because real-world performance only occurs in the real world, in real applications, with real customers and real infrastructure and the 17 network hops between you and the client. It doesn't mean that benchmarking is not valuable. Like, it's still nice to understand and valuable to understand what is the overhead of framework X. What is the theoretical maximum that I can achieve on a server of this configuration for this type of scenario as a result of this benchmark? There's a reason the TPC benchmarks, everyone know the TPC benchmarks, the database benchmarks, right? That companies are constantly vying and submitting multi-million-dollar machines to be run against the TPC benchmark, and so that they can show in that top 10. Okay? It's because people look at that as a source of information and then they make decisions based on it. The TPC one's really interesting because they actually show you the cost per transaction. They actually, part of submitting to the benchmark is say, I'm going to submit you a rack of servers and it costs $4 million. They go, okay, this is a $4 million system. And they run the benchmark and they cut out how many transactions per second was this system able to perform. And they go, well, okay, let's do some math. Every transaction cost you 0.00003 cents. Right? And so then you can directly compare systems for the same types of workload, OLTP, OLAP workloads, those type of things that you do in databases. What is the cost of this system versus that system when it comes down to raw throughput for the type of workload that I'm interested in? Okay? That's valuable information, right? It's really, really valuable. If you're going to make a decision, you have very large applications you have to build, and you want to know how much is it going to cost me to build a server that can run this application, that can do the load I want, benchmarking is a useful tool for that. It's not the only tool, but it is a useful input, it's a useful metric to have so that you can make those decisions. You obviously have to do real-world testing. And obviously for us, as the framework developers, benchmarking helps us measure our frameworks. We want to be the lowest possible overhead that we can be so that it's actually your applications that's the problem and not us, right? If there are performance problems, we want them to be yours, not ours. So this is a really, really important tool for us. We also want to be able to compare ourselves to our competitors, to other frameworks and other platforms in the world so that we know where ASP.NET stands. Why? Well, people look at this data. People look at these benchmarks and go, Node is fast. Who has heard that? Who has had people tell them, well, Node is really fast? Right? There seems to be a general sense that Node is fast because they harped on about this async I/O architecture from the very beginning. Now, we've always had async I/O in .NET, but it was hard. Like, Node did make it a lot easier, and it was built on that foundation. So people assume Node is fast. And it's pretty good. You know, it's not that it's slow, but we're much faster. Right? ASP.NET 5 is much, much faster than Node in raw benchmark numbers. And there are frameworks that are orders of magnitude faster again. Okay? Node is not that fast when it comes to the modern web landscape. But it's still faster than old ASP.NET by quite a measure. So the Tech and Power benchmarks. Who has had a look at these? Okay, quite a few people. Good. There's nothing wrong with looking at benchmarks. So these came to be, what about 4 years ago? Something like that. It's run by it's organized by a bunch of people, the Tech and Power company I believe they work for. And it's effectively they have a cadence of when they run benchmarks. You can see at the top here, round 8, round 9, round 10, and there's not particularly regular, but you can see they did round 8 in December 2013, round 9 in May of 2014, and then round 10 was basically 1 year later, and they're currently preparing to post the results for round 11. So, it's called a year in between runs here, okay? And it's completely open source. You submit your benchmark to GitHub, to their GitHub repository, and they accept it, and then when the next run comes around, they run it as part of their full run, and they post the results in here. And they do some interesting things. They have different scenarios. So obviously that's important. Like, what are we actually testing? All the way from like the most rudimentary plain text. So this is the plain text benchmark. And you can see like these are the type of numbers we're getting. 3.9 million requests per second. Okay, all the way up to 6.9 and then very quickly dropping off from there, you can see. Okay. And that's not a particularly interesting benchmark. That benchmark basically says, what is the overhead of doing HTTP on this stack? Right? It does nothing except accept HTTP requests, route them to code that handles that HTTP request, so it tests routing, and then respond with a certain number of headers and a certain payload. Okay, so you have to obviously test how efficient are you at writing I/O out, how efficient are you at composing headers, how efficient are you at talking HTTP? Okay? I mean, that's valuable, right? I mean, it's kind of nice to know how efficient is your stack at talking HTTP when you talk about cloud scale and massive things like that. And as you can see, there is a handful that are really good, and then there's everyone else. Right? And then, we're not even in round 10 because Windows didn't work in round 10. But if I go back to round 9, so we can see where we landed in that stack, there's the highest Windows result that they ran using a framework called Plain, which turns out doesn't exist. It only exists in this benchmark. I think it's an internal framework from some person at IBM that they submitted to the benchmark, but there's no way to use it other than decompile it from this GitHub repository and use it. So it's not real. And if we go down, we should be able to start seeing right down here somewhere. Here we are. Here's ASP.NET. 71,000 requests per second on that server. And that's a beefy server. That is a 48 core server, I think. 48 cores with 10 gigabit Ethernet. Okay, so there's really no bottlenecks when it comes to network. This is all about how much can you get with all that CPU. All right, we're terrible, right? Terrible when you look at us in the scope of this. And if you look at Node in here, which is the common one we get compared to, there's ASP.NET stripped. So that's ASP.NET, but we removed a bunch of modules from IIS and like config and stuff like that. This is a stripped down so you could get it 109. And then Node, I believe, is up here around 200. There it is. 290,000. So yeah, if you compare it to old ASP.NET, Node was much faster. But again, as I said before, things that are much faster. So that's plain text. And then there's more realistic benchmarks. JSON serialization. JSON serialization doesn't pipeline the requests. So it's not about just testing how efficient the HTTP is anymore. It's a little more real world. What if I just create a connection, I send a request, you do some stuff, and then I get a response, and then I send you another request, serially, back and forth. Whereas the plain text one is optimized to just make you do as much HTTP work as possible by sending you 16 requests at a time, and then you send me back 16 responses, okay? Which no browser does, but is interesting to test to test the overhead. So now we can see if you're doing something a little more real, and they have rules, like you have to actually allocate and do the serialization per request. You can't cache the response, for example, because what's the point in that? Why do we want to test caching? That's pointless. Let's test the overhead. And so when we actually start doing real stuff like JSON serialization, the gap starts to get even wider. Now the numbers go drastically down, but we still have frameworks that are hitting 1 million requests per second. Now that was C++. I don't think anyone's going to want to write their web app in C++, but look at what all these other ones are written in. Yeah. It's like 15 years ago, and our competitor has come back to haunt us, right? Java has really exploded as the foundational platform of choice for building really fast web servers. And it's not particularly because of anything Java did. There's a couple of things that they did that helped this, but it was more the open source community that really made this happen. And I'm very happy to say that with the work that we're doing now, we're getting some great contributions from the open source community in .NET to help us push Kestrel and subsequently ASP.NET 5 to hopefully be in these numbers as well. And I'll show you some of those in just a minute. And then the other ones we've got up here, then we start doing things like database queries. What happens when you run a request that does a database query to an actual database server? So now you need a whole other server. So now you're testing the latency and the processing time of the database as well. What if I'm doing multiple queries? Okay, so not just one query, but I'm actually doing a lot more work. And then finally, they have their fortunes test, which is the everything in the kitchen sink test. Right? It renders a view. It does HTML templating. It does updates and queries. It does requests from database. Pretty much it does everything you could possibly think you would usually do in a normal web application, and then they benchmark it. So right now, in ASP.NET 5, we've really only got as far as implementing benchmark implementations for plain text and JSON. Okay, we haven't got to the other ones yet. We do plan on doing it. The plain text, not that we haven't been doing performance work on EF and stuff, we have. But in terms of the end-to-end benchmark based on these scenarios, so far we're focused on plain text and JSON serialization. Which is good. So this is the foundation, right? This is Tech and Power. You can go and have a look at their benchmarks. This is what we've been using as one of our foundations for doing our performance testing. Let's go and have a look at, so we went through that. Let's go and have a look at one. So I've got a remote desktop here into my Smurf lab. I'm gonna have to zoom in here, obviously, because actually, maybe I should, no, I'll just zoom in, okay. So if you want to have a look at our results and where we're doing this work, go to the GitHub ASP.NET benchmarks repo, okay, up here, ASP.NET/benchmarks. And we've got a sort of two areas in here. We have the benchmarks folder, which is an ASP.NET 5 application that we're adding these scenarios to. JSON, plain text. We also have JSON and plain text using MVC. Okay, we have JSON plain text as pure middleware, and we also have JSON plain text as MVC, so we can measure the overhead that MVC routing and MVC add just to the standard ASP.NET pipeline. That's a really important measure, right? You want to know how much is MVC costing you for all that benefit. And then we've also got the same thing as a view right now. So we've got like a plain text view, right? So we can see how much does it cost to do MVC and then to invoke Razor as well. And then once we start doing the other scenarios, we'll add database in here and those type of things. And then we have a different area of the repository. Oops, I've gone too far back. Which is this one here, which is kind of fun. The experimental area. And this is where we try to set some baselines. Like we said, what would it look like if we just built the rawest HTTP server in C++, or based on HTTP/sys, or one based on the new Rio APIs in Windows 8, the registered I/O APIs in Windows 8. Still using C#, but we called through via interop into native code. Or what does it look like if we just run IS, right? Or other random ideas. And so we have some results. I'll show you the results in here. I think I've got these on my disk. It'll be easy to do. So if we come in here, GitHub ASP.NET, benchmarks, results, open my spreadsheet. Now this is not automated right now. This is basically done manually. I run these tests on the bench behind me. We have a bunch of desks behind me that have all these machines on them. And so here are, oh, where's my graphs gone? I don't think I have the latest. Hang on. Let me go and sync my repo. Let's do this. Source, GitHub, ASP.NET, benchmarks, git fetch, origin. Okay, let's try that again. Hopefully I have a new file. That looks better. Okay, so here is a comparison. So here's existing ASP.NET, right? So there's a bunch of numbers that are really small, basically, that you can't even read them. All right, so these numbers, if I hover over, I think it'll tell me. Nope, I have to scroll up and actually look at the data table. Here we go. So ASP.NET 4.6, running on the same server as everything else. Plain text, we get about 51,000 requests per second, okay? That's stripping out all the stuff that we can in IS. And then if we pipeline that, like we do in Tech and Power, you can see the number doesn't change. Right? We get no benefit to pipelining in the old stack because the overhead of the old stack was so high that by trying to send more requests, you just made things worse, if anything, right? Like, I have nothing left to give you. Why are you sending me more requests? I'm still busy doing the first one you sent me, right? We just don't have any more ceiling left. So then we start looking at some of the new stuff. So here's ASP.NET 5 Kestrel on Core CLR. Pipelining to depth 1 is 75. Okay, so and that's because on Windows at the moment we have a bug which limits the number of libuv I/O loops that we can create. We have a pull request out to libuv to fix this, and so we're currently limited with Kestrel on Windows until we get this bug fixed to how much I/O we can do at any one point in time because we only have one loop. But this number gets much better once we start pipelining. So here's ASP.NET 5 on Web Listener, running on Core CLR x64. We're getting 124, so we're already more than double what we were with ASP.NET 4 on IIS, which is nice. And then if we go down and we look at Node on Linux on the same type of machine, we're getting 131. So you can see we're in the same ballpark now, okay, with Web Listener at least. And then if I jump down to this one, here's ASP.NET 5 Kestrel on Windows Server, Core CLR x86, 443. And these numbers are actually old because I did a run last week, and we're currently hitting on Core CLR x64 on Windows. We can hit about 460. But instead of me saying that, let's just run it. Let's show you. So here's the Smurf lab, right? I'm in. And here's a PuTTY terminal over to a Linux machine that I use to generate load. We use a tool called WRK, which is the same tool that the Tech Empower people use. It's a very efficient HTTP load generation tool. We just need one box to generate this load. That's all it needs. The tool is so efficient that we can simulate tens of thousands of connections if we need to, and get millions and millions of requests per second from just one box. We have a 10 gigabit Ethernet switch in between these 4 boxes. So I have 2 Windows boxes and 2 Linux boxes. And that switch is isolated from the rest of the Microsoft corporate domain, right? So normal type of thing you do when you're doing benchmarking and load testing. So let's actually run a server. So that one's a Java server. I'll show you that one in a second. Let me come into my benchmarks repo. And let's just hope this runs. Let's hope nothing breaks, because it's been a while since I've updated. Okay, so that's running, 5001. I can prove that. Let's come up to the browser, and I'll hit the... So there it is. That's the internal IP address for the 10 gigabit Ethernet cards, because they're not on the wider network, right? So hello world. So let me run a benchmark against that. We'll come down into PuTTY. I will first warm it up. Whoops, sorry for jumping around so much. I'll warm this up. So I'll just give it a very simple workload first. 32 connections, no pipelining, and I'll just run it for 5 seconds, okay? So I'm just going to run that, and I should see over here, a little bit of work happened. Okay, not much. I'm just warming the thing up, priming, caches, those type of things. Then we'll come in here and I'll do a little bit more load, okay? So let me click in here. Let's make it about, I usually run these about 256 connections, which is the same thing that Tech Empower does. And I'll run this for 10 seconds this time. And this time I'm going to pipeline to a depth of 16. And that's what the plain text benchmark in Tech Empower does, because again, the purpose of this benchmark, this scenario, the plain text one, is to test how efficient you talk HTTP. That is the purpose of this test, with the overhead of your application framework. So this has a startup CS, it's Project JSON, it's an ASP.NET 5 app, and it's doing routing, not MVC routing. It has middleware that says, if the path starts with /plain text, run this bit of code. All that is happening in this application, okay? So let me zoom out. So I can show the CPU at the same time. There it is. We'll hit enter. And so you can see immediately I've got 100% CPU, which is good, and I'm doing about 360, 370 something megabits per second. And we'll see what that equates to. And this is an issue I have in my test lab at the moment. Sometimes I need to restart the Linux boxes in order to get the performance. So I think this box needs a restart. The 311 isn't bad, but it's not great. We should be getting about 480. And that's because that Linux box needs to be restarted last time I checked. Right, but that's still interesting. But what are we up against? Like, what are we actually trying to achieve here? Let me stop that server. All right, so that one stopped. Let me go over to my other PowerShell window here. This is another server. This is Netty. Anyone ever used Netty? Even if you haven't used Netty directly, you've probably used Netty if you've used a myriad of other server technologies that are built on Java. Like Netty is used in a lot of well-known products, okay? A lot of well-known sort of box products that you use, or a lot of things you install to do other stuff. and it's incredibly efficient. So here's my Netty server running on 8080. So let me do the same thing again. I'm not even going to bother warming it up because I'm not going to give it that luxury. So I'm just going to hit it immediately with a bunch of connections, and we'll see what it's doing. All right, so we're hitting 3.3 gigabits per second. All right, so that translates to, call it 2.7 million requests per second. Okay, so that's the type of thing that we're up against, and that's what we're aiming for. Okay, to be absolutely clear, that's what we're aiming for. There is no reason that we cannot achieve these results. There's just no reason for it. Java has an I/O library that's built into the Java standard library, has Neo and Neo 2 and a bunch of other stuff. They implement that on Linux, they implement it on Windows using the native APIs on those platforms. You know, I/O completion ports on Windows, Win32, WinSock, and on Java, EPOL, and all those good things, KQ. And then they give you a nice API, and they have some nice buffer management stuff in Java that you can build nice things on top of. Now, the API for using Netty isn't particularly nice, but there are other Java frameworks like Undertow that perform just as well, if not better, and their code looks like ASP.NET 5. Like if you look at the code to write the plain text handler, if you squint, it just looks very similar to an ASP.NET 5 middleware. So this is totally possible. And we are currently, as I said, we've probably just about hit 500,000. We've got a bunch of pull requests out right now that improve memory allocation that will get us closer to about 550. And then we need to start looking, when we go back to the profiler, we run profilers, we're using .trace a lot for doing this, and we look for the next big thing that's going to get us our next big gain. But as you can see right now, I mean, we have to improve our throughput by about 5 times to get close to this. Yes?
What's your bottleneck right now? Is it I/O or memory?
So the question is, what's the bottleneck right now? We don't know. We have to profile. So we're at this point right now, the assumption is that we are allocating too much memory. So if I was to show you the .NET memory counters while I did the Kestrel test, it would show that on x64 core CLI, we're allocating 1.3 gigabytes per second. That is too much, right? Because especially if we want to go 5 times that, we can't allocate 6 gigabytes a second. Like, you just can't do that. It's just too much. So we need to pull more. We need to more efficiently use buffers. We need to have more memory efficient algorithms for doing things like encoding. Like, how do we take some objects, like you added headers, and then on the way out, we need to turn those .NET structures, like strings that are 16-byte structures, UTF-16, or typed information, numbers and things, we have to turn those into ASCII bytes for headers. That process costs time, and there are various algorithms you can use to make that cheaper, and you can use more or less memory to do that. The less memory you use in doing these type of things, the faster you'll generally end up going. And so we have crazy code. So like Lou added code that uses SIMD. Does everyone know what SIMD is? Single instruction, multiple data. Who's ever heard of SSE or MMX in Intel processors or AVX? Right? These are the extended extensions in CPU architectures that let you give it some data and then issue a single CPU op command and then have it parallelize that command over the data, but you only wore the cost of a single CPU instruction. So, and depending on how wide that pointer is, that data structure, the more parallelism you get. So like on AVX, I think it's a 32-bit wide structure, and on AVX2 it's 64-bit wide. So you can get 64 levels of parallelism if you're operating on bits, whereas previously you would have to have done 64 operations, right? Massive reduction. We're using the system.numerics package, which .NET released last year, which enables you to use SIMD in .NET applications if you're using the new jitter, the Ryu JIT, which is in .NET 4.6. We're using that to parse headers. So as the bytes come in off the wire, we have some crazy code that looks at bytes in chunks of, I think it's 8 bytes at a time or 4 bytes at a time or something, and then we pattern match them using SIMD instructions so that we can get the most common header parsing done in 3 or 4 operations instead of enumerating through every single character. Right? That's the level of stuff you have to get to these type of numbers. And like I said, we still have 5 times the performance to go. But I'm confident we can get there. Like, I still think there's a lot for us to do to get there. Now, that's the really core stuff. Very soon, we will add more complex Razor views. We are already doing a lot of work in Razor memory allocation in isolation. We will add end-to-end EF queries in here as well with a real database behind it. We'll probably do Postgres to start out, and we'll add SQL Server as well. I know the EF team has an automated performance sort of bench where they do more micro benchmarking for regression testing purposes, so they can ensure that they don't introduce performance regressions, and we will rely on this type of infrastructure to give us the more end-to-end benchmarking or platform benchmarking stuff. So that's what I wanted to show you. We care a lot about performance. We're doing a lot. We have a lot more to do. We are very welcome to people sending pull requests to the frameworks that we have. One particular guy, Ben Adams, at the moment in the community, who is sending lots of fantastic pull requests to all the various parts, HB abstractions, the hosting layer, Kestrel, the benchmarks repo, and really trying to drive up these numbers by driving down the memory allocations and the compute being used. So yeah, it's kind of exciting time if you're into that sort of really geeky performance type stuff. But we care about it, we're working on it hard, and those are the type of things that we're going after. Yes? Mm-hmm.
Having to go and app startup, which is sort of counter to the idea of performance being focused. Because every time you go into app startup, it means to make these changes, I have to incur that startup overhead of rebuilding the app tool, reloading memory, reloading my application, right?
So okay, so I guess your comment is more about developer time performance, like the developer workflow, the performance of that? What's that?
Recognizing that there are things that happen in applications.
Yes.
Where applications are doing dynamic loading of plugins or dynamic loading
Sure.
of other code.
Yep.
And at runtime, you want to be able to change behaviors of the underlying platform.
Sure. So the comment is, it seems that with the push to the startup concept, where you're doing a lot of work to set up the application once, that seems to be at odds with the idea of being able to have apps react quickly to changes underneath them if they're a little more dynamic in nature, like they're loading modules and things. I wouldn't conflate those two things. To give you some examples, MVC views can still compile on the fly without recompiling the application, right? I add MVC once, I set it up in my pipeline. MVC includes in it a compilation system that allows it to discover new files that you drop on disk or changes to files while the app is running and recompile them on the fly without you having to start the app. And if you've ever, like right now when you use MVC 6, and once you've got the app started, if you make a change to a Razor file and go back to the browser and hit F5, it is instant. Like it is absolutely instant because it can recompile that one file very, very quickly. Similarly, the configuration system in RC and the logging system in RC and the templates will be set up such that they can dynamically reload themselves while the application is running, based on files changing, for example, or based on code that you write that causes them to reload when you detect that something has changed. So the templates will be set up such that logging is set up nicely. We log stuff out to the command line. The logging is configured by a configuration file in the template. And while the app is running, you can change that file. And as soon as you save it, the logging system reloads its configuration without you having to restart the app. So we are very mindful of those type of things that you want to be able to change. And if you want to build a system whereby the app can discover dynamically modules at runtime, you're still free to do that. It's always a trade-off because there's obviously cost associated in doing that. It's more complex code to write. But we do have those primitives available in the system that you can watch files, you can do compilation on the fly, but you can't do things right now like affect the application-wide dependency, the IC container though, right? That is set up during app start and that lives on forevermore. But okay, I hear you. All right, I'm over time. That's 1 minute in. So Rowan's turn. That was performance. If you've got any questions about performance, anything a little more specific or just general comments, by all means, grab me when you see me later on in the day.